Thank you for attending this presentation. Today I'm going to introduce our work, Truly Black Box Attack on Reinforcement Learning via Environment Poisoning. In this work, we studied the question that the training time attack on reinforcement learning in double black box settings. Here, our goal is to induce a black box RL agent to learn a target policy which is designed by the attacker in a black box environment. So to achieve this goal, we will manipulate the environment dynamics during the agent's learning process in order to drive the agent to learn in a specific direction. And the problem is interest that if we have no idea about how the agents learn its policy, and if we don't know how the environment responds to the agent's specific action in the learning process, how we can drive the agents to learn a specific policy in the unknown environment. So in this work, we propose the approach to induce an unknown agent to learn a target policy in the unknown environment. First, we will introduce the background why we started attacks on reinforcement learning. With the wide adoption of reinforcement learning in the real-world applications, the security issue has become more and more important in critical applications, such as the self-driving, financial trading, healthcare. So if we can understand how the RL agent is vulnerable to the adversarial attack, it will help us to find the mitigation procedures before we implementing the RL into the critical applications. So since the 2017, adversarial attacks had started by more and more researchers, and the existing work can be classified as two parts, test time attack and the training time attack. For the test time attack, here the agent already learned its policy and fixed its policy. And when it uses its policy, the attacker wants to degrade the deployment performance of the policy by providing a perturbed state to the agent in order to mislead the agent to choose a suboptimal action or a target action. So in this way, the agent's performance is degraded, but the agent's policy itself has not been changed. And different from the test time attack, in the training time attack, the agent's objective is to change the agent's RL agent policy itself. So the attacker needs to interfere with the agent's learning process. For the existing work, the attacker generally changes the reward signal between the agent and the environment, and some work choose to manipulate how the environment responds to the agent's specific action. So because the attacker needs to interfere with the agent's learning process and drive it to a specific direction, in most work, the RL agent is assumed to be a white box. This means the attacker can assess the agent's perception and knowledge in order to get the complete interaction between the agents and the environment. And then the attacker also knows the agent's learning algorithm and the policy model. In this way, the attacker can design a specific attack strategy for a specific learning algorithm. But actually, in the real-world application, this two information is generally protected and cannot be accessed by the attacker. So to make the training time attack more practical in real-world application, one work transferable environment poisoning attack has been proposed, which are effective for both white box and black box RL agents. And in this work, it chooses to manipulate the physical property of agent's external environment in order to manipulate how the environment responds to the agent's specific action during its learning process. And the second, this work is also effective for black box RL agent due to its transferable property of the poisoned training environment. This means that even though the attacker has no idea about how the victim agent learns its policy, but it can design an attack strategy based on a white box proxy agent and then transfer the attack strategy to attack a black box victim. So this work overcomes the assumption that RL agents should be white box. But this method is developed based on one assumption that a attacker needs to know how the environment responds to the agent's action. This means they need to know the environment dynamic models and the stationary state distribution. And here the attacker is assumed to is a required white box training environment. But actually, in the real-world complex application, the model of training environment is not easy to be known by the attacker, even by the agent. So this assumption constrains the scalability of this proposed work. So based on this table, we can see that the TIPA removed the two assumptions of the compared with the white box. But in our work, we also removed the assumption that the attacker knows the dynamic model of the victim training environment. So the motivation of our work is study the training time attack on reinforcement learning in the double black box settings. Here, the one black box is the RL agents. We don't know how the agent learns its policy and what is the agent's momentary policy during its learning process. And another one is we don't know how the environment models. So the training environment is also black box to the attacker. So in the double black box settings, we want to force the unknown RL agent to learn a target policy in the unknown environment. And in this work, we inherit the attack framework and pursue the same attack objective as the TIPA. Here we formulate the attack problem as a bi-level Markov decision process. Here both attacker and victim are formulated as RL agents. And we can see that here the victim agent is a normal RL agent that is only want to pursue is maximize the cumulative rewards and get the optimal policy which can pursue its own benefits. But for the attack level RL agents, its objective can be summarized as two parts. The first one is it wants the victim agent to learn a target policy, which is designed by the attacker. Another one is it wants to control the cumulative changes of the environment in order to avoid being detected. And here from this figure, we describe the workflow about the attack. During the victim's learning process, the attacker will observe the victim's policy and the environment transition probabilities. And then based on these two condition information, it chooses a responsive attack action in order to drive the agents to learn in a specific direction until the victim learns the target policy. So based on the objective of the attacker, we can see that the attacker wants to minimize the difference between the target policy with the victim's actual policy. Another one is want to minimize the deviation between the default environment and the manipulated environment. So when we combine these two components together and represent it as the stochastic process of the victim, so the attacker's objective is to minimize the deviation between these two stochastic processes. So the optimization objective of the attacker is to minimize the cumulative attack cost, and this attack cost is defined as the deviation between the ideal stochastic process with the actual stochastic process. So in this problem, we want to learn the attack strategy, which is conditioned on the victim's policy and the momentary environment transition probabilities, and it wants to minimize the deviation between these two components. Black box settings, there are two problems to solve. First, the attacker don't know the condition information of the attack strategy, so we need to capture the latent representation of the victim's policy and the dynamics features. And second, because we have no idea about these two components, we cannot compute the attack cost directly, so we need to propose the one method to approximate the attack cost in the latent space. So in this work, we propose the attack procedure in two stages. First, the attacker needs to capture the representation about the victim's stochastic process based on its trajectory samples. And here, The latent embedding can capture the features of the victim's policy and as well as the environment dynamics. And based on this latent embedding, the attacker will choose a responsive attack action which can manipulate the environment dynamics. And then, based on the attack procedure, we can see that for the training of attack strategy also includes two parts. One is how we learn the latent representation of the victim's stochastic process. Another is how we learn attack strategy. For the latent representation learning, we proposed one in order and dual decoder in neural network. And here, the encoder is a LSTM network, and for the decoder, there are two parts. One is policy decoder, which interprets the condition on the state and output the action. Another is the dynamics encoder, which interprets the environment dynamics, the next state condition on the state and action. And in this way, we can learn a latent representation Z, which represents the information about the environment dynamics from the transition sample, state, action, and the next state, and then can also capture the policy features from the sequence of state action pairs. So this latent embedding can be input as the attacker can be input as the attacker's input. Second is how we learn the attack strategy. As our definition about attack codes, we want to measure the difference between the stochastic with the ideal stochastic. So we approximate their deviation in the latent space and use the cosine similarity to measure the embedding Z and the Z star with the cosine similarity defined in this way. So in this work, we provide a preliminary experiments to show that our proposed method works well in comparison with the baseline TIPA. And we choose the same environment as the baseline, which is a 3D grid world. And here the elevation change is a way to manipulate environment transition dynamics. The success of moving from one cell to the other depends on the relative elevation between these two cells. And here the blue line represents the optimal policy, but the red line is the attacker's target policy, which means attacker wants the agent to reach the destination along the border of the grid world. And for the first result, we compare our method with the baseline white box TIPA. And here the x-axis is the victim's learning process, the time step, and attack success rate means whether our victim can perform the desired action in the target state. And from this figure, we can see that our method performed quite similar as the baseline. This means in the double black box settings, our method can force the unknown agent to learn a target policy in the unknown environment. Second is we learn an attack strategy which is learned on the black box victim in unknown training environment. And here the black box victim is actually learned using the Q-learning algorithm. And then we use this attack strategy to attack another black box victims in the same training environment. And from this figure, we can see that all of these black box victims can achieve the target action in the target states at the end of their learning process. So this means our attack strategy is insensitive to the victim's learning algorithm, and it's effective for different algorithm-based victims. Compared with the baseline. In the baseline, it requires the environment dynamics model, and when it's used for the black box agent, it needs to learn the attack strategy on a white box proxy agent, and then transfer it to our black box victim. But in our work, we don't need to depends on the environment dynamics model, and don't need to depends on transferable learning capable white box proxy agents. Here, we just train the adaptive attack strategy directly on the black box victim, and this attack strategy is also effective for different black box RL agents. So this is a work developed in process, and in this work, we started training time attack in the double black settings, where the agent's learning algorithm and the agent's environment dynamics is unknown by the attacker. And this setting is more close to the real-world application, so we called it as the truly black box attack. And then to solve this problem, we proposed the latent representation of the victim's stochastic process based on its trajectories, and then learned the attack strategy based on the approximation in the latent space. And in this work, we only present a preliminary experiment to show the attack strategy is effective for different black box victims in one unknown environment. And in the future, we will evaluate our proposed method in more complex and more realistic environment. And thank you for your attention. Welcome for further discussion.